Up to this point, we focused our discussion primarily on what we call monoprotic acids, so acids that have a single proton that can react with water. And we know that these acids undergo an acid dissociation reaction to produce the conjugate base and hydronium. Okay, and as we all know, this is governed by a Ka, which is related to a pKa. But as it turns out, there are lots of examples of acids that have more than one proton that's able to be that can be ionized. So in this case, we can think about a diprotic acid. So diprotic, so di meaning two, protic meaning proton, so two protons that are reactive. We might represent this as H2X. So since this is diprotic, we have two ionizable protons. So once the first acid dissociation reaction occurs to produce one equivalent of hydronium, we'll call this Ka1, then this product can further react with water through another acid dissociation reaction, and here we produce the conjugate base X2- and another equivalent of hydronium. And this acid dissociation reaction is governed by the second Ka. So there are lots and lots of examples of diprotic acids. Two we can think about would be carbonic acid, so H2CO3. This is really important in the buffering capacity of your blood. And another one might be H2SO4, right? So sulfuric acid. Each of these we see here show two protons in front of our common polyatomic ion. So they're both diprotic. And since they're diprotic, they have two Kas and therefore two pKas. So we would have pKa1 and pKa2. So what we want to do in this video is focus on a couple main ideas here. One is, let's see how this idea of a diprotic acid influences the titration curve of a diprotic acid. And two, let's think about how these two sequential acid dissociation equilibria can influencing the buffer ability of a diprotic acid. Okay, so let's do the titration curve first. Okay, so we're going to go ahead and start this and think about this in exactly the same way as we've done in the past. Right, so we have on the y-axis we have pH, and on the x-axis we are adding sodium hydroxide. So the concentration of sodium hydroxide is increased as we move to the right, and we're becoming more basic as we move up. So the things that we really want to focus in on here are the first half equivalence point and the first equivalence point. So this very first equivalence point is when we've converted all of our H2X to our HX minus. Alright, so we've reached our first equivalence. We've converted H2X completely to HX minus. We can then go through a second equivalence point, or a 3/2 equivalence point, and then our equivalence point number 2 is when we've converted all of our monoprotic acid to X2 minus. So we know at the first half equivalence point, just as we've learned in the past, this is going to be our first pKa, so pKa1. And then at the second half equivalence point, this will be where we're at our second pKa, so pKa2. Alright, so then this curve ends up taking the shape just like we've seen in the past. We have a reasonably sharp curve, and then it slows down going through the buffer range. And as we reach the end of our buffer range, we have a sharp transition. Going into the second pKa, it levels off going into the buffer range. We go through our pKa, and then we transition out into our sharp inflection. So the first half equivalence point occurs at the first pKa. The second half equivalence point occurs at the second pKa. And as it turns out, this pH at the equivalence point is exactly the average of pKa1 plus pKa2. So this would be pKa1 plus pKa2 over 2. And that's how we can determine exactly what the pH is at this equivalence point. So let's put some numbers to this. So carbonic acid. H2CO3. It has the first pKa, so pKa1 is 6.35, and pKa2 is equal to 10.33. That's a 10. Okay, so on our titration curve then, we would have our first pKa at 6.35, our second pKa at 10.33. And the pH here at our first equivalence point is going to be the average of these two. And that value is 8.325. So in terms of predicting what a titration curve for di or tri or polyprotic acid, these are the things you want to think about. We know that for every acid dissociation reaction we have a pKa, and each pKa has a buffer range, right? So we have our first buffer range centered around 6.35, our second buffer range centered around 10.33, and the pH in the middle at the equivalence point is the average of these two. Let's try one more. Let's try a triprotic acid. So we'll do phosphoric acid. So phosphoric acid has 3 pKa's. So pKa1 is 2.16, pKa2 is 7.21, and pKa3 is 12.32. So if we were to sketch a titration curve for phosphoric acid, we would have 3 buffer ranges. So our first buffer range is going to be centered around 2.16. Our second buffer range is going to be centered around 7.21, and then our third buffer range will be way up at 12.32. So there's the first half equivalence point, there's the second half equivalence point, and our third half equivalence point will be way up here. So then this curve will look something like this. We have our sharp transition, we go through the second buffer range, sharp transition, third buffer range, and then it'll kind of flatten out. Alright, and just as we saw before, we can figure out the pH at these equivalence points. So the first one is the average of 7.21 and 2.16, which is 4.69, and the second one is the average of 7.21 and 12.32. So this would have a pH of 9.77. So we'll stop here for this first video. In the next video, we'll focus in on the buffering properties of these polyprotic acids.